One is what I just demonstrated is that the modern sort of irony of technology and productivity. What I just demonstrated is that everyone here wasted about 5 minutes for us to be able to bring up the technology. So this is the reason why one of the very famous professors from our department, Dick Blahut, Professor Blahut mentioned once in one of the faculty meetings that if the computers were invented 1,000 years ago, and then people just recently discovered paper, and paper would have been viewed as the most important invention in history. And the reason is paper oftentimes will improve our productivity over technology, computers, and so on. And if you think about it, all the teleconferences that we use, no matter which type, always waste us about 5-10 minutes for someone to turn on the audio, or someone cannot get the connection right. So you know what? This is something that people in this room will fix in the future. And maybe one of you will discover the old telephone lines, and I will actually fix all these problems. But it's kind of one of those modern ironies that I think all the engineers should think about as you pursue your career. So I lectured from Chicago last Thursday, and we finished the tile convolution, and hopefully everyone has finished the MP for that. How many of you finished the MP for tile convolution, MP4? And so, you know, let's make sure that you're really done. And today I'm going to continue what we started last time, the analysis of tiled convolution algorithms. Okay. And hopefully we will end early enough that I will begin to lecture into the feed-forward networks and work ourselves into the neural net implementation. We already learned both foundations that we need to be able to implement neural net. The first foundation is matrix multiplication and tile matrix multiplication. And the second one is convolution and tile convolution. And so these are the two primary implementation techniques that the experts in the field today use to implement neural network frameworks and so on. So you're pretty much positioned to do that implementation. And after we finish the sequence of neural net implementation lectures, we're going to go back and begin to go into the reduction trees and scan algorithms and so on. Keep in mind that the world does not only have neural nets, okay? As much as all of you are so excited about artificial intelligence, neural networks, deep learning, and so on, keep this in mind. The world has many, many other computational problems and many, many of these algorithms that you need to be aware of. So we're going to go back and teach the foundational algorithms for many types. And as you have the time to begin to think about your final project, okay? Hopefully this is one of the changes we made this semester to give you more time to be able to be creative in your project. So last time we started to go into the analysis of tiled convolution algorithms, and so this is one of the slides that we already covered for one-dimensional convolution. We're going to have when we calculate an output tile, which is the solid, in this case, the output tile is 8 in this particular example, and if the mask width is 5, the radius is 2, right? So we're going to have 2 elements on the left side and 2 elements on the right side. And this gives us an input tile of 12. So 8 elements in the output tile and 12 elements in the input tile. So one of the ways that we can calculate the memory access efficiency is by thinking about how many times will each input element be used when we load that into shared memory. Because every time it is used from the shared memory, you replace one of the global memory accesses with shared memory access. So you eliminated a consumption of the global memory bandwidth. So if we look at this particular example, element 8 in this example will be used by to calculate element. Actually, we can do it from the output point of view. The output element 8 will be calculated based on 5 input elements. That's what convolution is about, right? The 5 nearby input elements. So 6, 7, 8, 9, 10. So if we look at it from the output point of view, we're going to be able to tally up all the input elements that are accessed for calculating every element of the output tile, right? So I don't know how many of you remember the physics problem that you guys probably have in your junior year in high school or senior year in high school, depending on the high school you came from. When we calculate the speed and so on for these objects going down the river, there are usually 2 views. Okay, one view is you stand at the bank of the river, you see the object going by, right? And the other one is you stand on the object in the river and you see things going backwards in the river. And you can calculate the momentum and you can calculate the kinetic energy in either view, and you should get the same result. But sometimes it's easier to go from one view rather than the other view, right? So in this case, we have exactly the same situation. We have, we can look at the memory computation bandwidth from output point of view. Essentially, for every output element, it's going to be using so many input elements. And we can see that all the elements, once we loaded the tile into the shared memory, all these input elements will be accessed out of the shared memory. And we can also calculate how many input elements will be loaded into the shared memory. So that gives us an improvement ratio. So this is exactly what we're going to do. We say that in the original algorithm, when we calculate output element 8, we're going to be using N6 through N10. All those would have been global memory accesses. And P9, same thing, and so on. So a total of 8 times 5, which is 40 input elements, would have been accessed from global memory if we didn't use tiling. Right? Those are the accesses we would have made to the global memory. And then if we use tiled algorithm, let's say strategy 2. And in strategy 2, we're loading all the input tile elements into the shared memory, right? Everything that we need to calculate the output tile, we will load into the shared memory. And what that means is we need to load the core of the input, the core of the tile plus the radius, right? So we're going to be loading 8 times 2 on each side, so which is 12. So that's 8 plus 5 minus 1, because that's the radius. That gives us both radius, from the both sides. So we need to load 12 elements in order to enable the loading of every element from the shared memory. So we have 40 global memory accesses replaced by shared memory access, but we need to pay the 12 loading upfront in order to be able to, to achieve this kind of savings. So the bandwidth reduction is what happens beforehand, which is 40 global memory accesses, right? If you didn't use tile access, 40 global memory accesses will be done. Afterwards, before and after, right? The after is that you only need to load 12 of these elements into the shared memory, and then you'll be done with that the global memory accesses. So the total bandwidth reduction is 40 over 12, which is 3.3 times reduction. Sometimes people prefer to say it's 1/3 of the original one. But usually when we do the kind of the reduction or speed up and so on, we usually take before and we take after, we take that ratio. So, it's kind of like some of the commercials, right? When they say, before, after picture, and then look at this. This is great, right? So we do exactly the same thing here, but with more engineering principle, right? This is just, one of the fundamental things that we do to show the benefit of the process, okay? So this is where we were from last time, okay? And in general, if we generalize from the the exact sort of the small number of 8 elements in the output tile and 5 by 5 mask, we take general tile width. So tile width was equal to 8 in the in that small example, and mask width was 5 in that example. But now we abstract it. We take it out and say, okay, if I have any kind of tile width, okay, arbitrary tile width and arbitrary mask width, what would be the savings that we can make out of our strategy 2 algorithm for 1D? And it's very intuitive. If we didn't do tiling, we have the output tile P elements, right? The output tile has, tile size output elements. Each of these elements will need to access the global memory mask width times. So the total number of global memory accesses in the basic algorithm will access tile width times mask width global memory accesses. Okay? After means that we're going to be loading the size of the input tile. The input tile is just the output tile width plus mask width minus 1, because that's the radius on each side. So we take these two expressions, we take a division, and that gives us the general formula for savings, right? For memory bandwidth savings when we go from basic to tile. This kind of expression, if you know exactly what it is, if you know the expressions, if you know how this is derived, when you look at this, you will immediately be able to tell exactly, which term it came from, and so on. And so this is the reason why a good, well-trained, well-educated engineer will not be afraid of looking at expressions, because these expressions should be just a reminder of the thought process that we have been through, right? But for those who did not go through this kind of education and training process, this looks like gibberish and something that just doesn't make any sense, right? So this is the reason why engineers should not be afraid of math. None of you should be afraid of math. Once you understand exactly what the math represents, math becomes your friend. Okay, so make sure that you really, really understand all the derivations and all the concepts that expression represents. Now it represents friendship. Okay, now it represents warmth, and it represents insights. Okay. There's another way to look at this. Another way to look at this is look at it from the input point of view. So remember when I said this thing about object going down the river? So now we're going to analyze it from the input elements point of view. These input elements will be loaded into the shared memory up front, and each input element will be used for calculating multiple output elements, right? So, so in the previous analysis, we look at each output element and say, in order to calculate this output element, you need to access 5 input elements each. Okay? Now we say, once we loaded the input element into a shared memory, how many output elements will be using this input element? So how many times each input elements will be used? And so if we add up all the accesses to all the input elements, it should also give us the savings, okay, that we got from loading these elements into shared memory. So we say, okay, input element 6 will be loaded into the shared memory, but input element 6 is not going to be used to calculate many output elements. The only output element that will be using element 6 is actually just P8, because 6 is one of the halo cells. And only element 8 at that very edge is going to be using that input element. The calculation of any other elements in the output tile will be too far away from N6 that they will not be using N6. So in many ways, when we load the N6 into the input into the shared memory, we just broke even. Okay? This element was not the best deal. When we spend the effort to load it into shared memory, and then we only save one global memory access later on, right? This barely breaks even. So this is not the best deal among the whole group. If I look at N7, N7 will be used by two output elements, okay? P8 and P9. The others are too far away, okay? So if I continue this, this audit and say, okay, you got into shared memory, how many times were you accessed? Justify your existence. Justify your, seat in the input tile, in the shared memory. Each one will say 1, and then N7 will say 2, okay, and then 3, and 8 will say, oh, 3, so is 3 a good number? Not quite. N9 will have 4, and N10 will have 5. If you're looking to a big enough input tile, that 5 will be there for a while. Several input elements will be used by 5 times. The reason is, nominally, all the input elements should have been used 5 times. Okay, should have been used 5 times. However, it's because the input elements are so close to the outside the core and so far away from the inside that these elements only are going to be used for this output tile. For this output tile, only once or twice or 3 times. Remember that same input 6 and 7 would also be loaded by another thread block, right, to calculate another output tile, the output tile before this output tile. And that will be loaded into the shared memory of a different thread block. So the reason why they're only used 1 time, 2 times is because they also are used 1 time or 2 times or more by the other thread block. Okay, so that's why you are spreading out the 5 times of usage of these input elements into 2 thread blocks. Okay, and this reduces the memory the memory efficiency improvement that you can make. Does that make sense? Okay, and this goes back to to one of the questions in matrix multiplication. One of you asked me, what limits the memory reuse out of the shared memory for matrix multiplication? I said it's the thread block size, because the tile size determines the number of times each element is used, and these elements need to be also loaded into other thread blocks, and those thread blocks, each thread block can only give you tile width times of reuse in the matrix multiplication. Here, the limitation is you have these halo cells, and these halo cells usage are spread across 2 shared memory, in 2 adjacent thread blocks, and these need to be separately loaded into the shared memory, and therefore limiting your reuse. And when we calculate some of the trends, it will become even more clear, okay? But any question about the input element view? Every input element loaded into the shared memory will have a number of uses by the calculation of the output element in the output tile, right? So we listed all these input elements, all the 12 of them, and each one will be reused from 1 time to 5 times. And we notice that from element 10 to element 13, all of them are reused 5 times. These are what we call the real core input tile elements. These are the elements that are truly used by 5 of the output elements in the output tile. Okay, these are at the very center of your input tile. So now you see that the input tile elements are not born equal. Okay, some of them are very, very highly reused, and some of them are not quite highly reused. Life is not fair for these input elements. Okay, now we can calculate the reuse from another way. This way you say each time an input element is used, it replaces an access to the global memory and element. Therefore, if we add up the number of times each input element is used, it should also give us the number of global memory accesses that are eliminated by loading all these input elements. So we can add up 1 time for input element, 1 one time for that input element 6, 2 times for input element 7, 3 times for input element 8, and 4 times input element 9, and then input element 10 5 times. And then we will continue output tile width minus, essentially output tile width minus the mask width plus 1. This is the number of elements in that true core, the true core of the input tile, okay? And then you go back down to the right-hand side, 4, 3, 2, and 1, okay? So the intuition here is that whenever we have a tile width, we're going to have tile width minus 1 elements on this side that will go from 1 times to mask width minus 1, okay? And then we have another side going from tile mask width minus 1 down to 1, right? And then you take the input tile width and subtract those two sides, and you get tile width minus mask size plus 1. So this is how you can derive the core section, the left section, and the right section of your tile, okay? You add them all up. This side, 1, 2, 3, 4, 5, you add up, they add up to 10. This side is exactly symmetric, so you should also add up to 10. And the middle part is 5 times 3 plus 1, 4, so they get 20. So you replace a total of 40 global memory accesses, okay, with the shared memory accesses. So this gives you exactly the same answer, right? From the input tile point of view, I added up the number of accesses to each input element, I get 40. Another way to look at it is I add up the number of input elements each output element needs, and I also add up to 40. The output element view is simpler because every output element uses 5. It's very uniform, easy to calculate. If you look at the input elements, life is not fair. Some of them are small, some of them are big, but if you add up the expressions, you also get 40. Right? So these are the two views. Both are valid. Use whichever view is convenient. So we still load the 12 input elements in the tile algorithm. So the ratio is still 40 divided by 12, 3.3. So this is the beauty of engineering, the beauty of math, beauty of physics. No matter which view you use, you should get the same answer. Okay? And use whichever is more convenient. So now, if we look at the ghost elements on the side, there's something slightly surprising about these ghost elements. Remember, in our policy, whenever we need to use any of the ghost elements, we're going to just assume they're 0. So we're not going to be accessing memory. We're going to just use 0 value, okay, for their calculation. So even with a base algorithm, in the basic algorithm, whenever we're calculating an output tile at the edge of at the edge, they're not going to be accessing global memory for the ghost cell. They're going to just use 0. So there's no global memory access to replace for these ghost cells. And also, when we load them into the shared memory, we don't use access global memory either. We just place a 0 into the shared memory. So if we look at the boundary tile, we only load the tile width, the output tile width, which is the middle part of the input tile, and we only load half, the right part of the halos into the shared memory, right? So this gives us tile width plus mask width minus 1 over 2. We usually have another one on the left, but we don't load them, right, for these ghost cells. And if we look at the computing boundary, the sort of calculation of the output element for the global, for these ghost cells, we also have the same thing. We're going to be, accessing the total access is actually just 3 plus 4, because when we calculate the output elements, not all the output elements will access 5 global memory accesses. The left edge output tile element only access 3 input elements, the itself and 2 to the right. The ghost elements are not being accessed. So we have one output element that only uses 3, and then the one next to it only uses 4, and then the rest will still use 5. So this gives us 3 plus 4 plus the rest, which is 6 of these output elements on the right part that still access 5 global memory accesses. So this gives us a total of 37 global memory accesses that we will be doing for, for the output tile that is at the left edge of your 1D convolution. So 37 accesses in the basic algorithm over 10, over 10 in the loading of that tile. So this gives us 3.7. So the interesting part is, when you look at this, the reduction of global memory access, the ratio is actually slightly higher, right? To some people, this is a little bit surprising because, if you're not doing as many global memory accesses, you should have, probably have maybe a little less reduction when you load the tile into the shared memory. But remember, when you load the tile into the shared memory, you also avoided some loading. And that rate, the portion that you don't load into the tile is slightly bigger than the portion of the global memory accesses that you avoided for the ghost access. So that's why you get slightly bigger. But it's not significant enough to really worry about. Okay? It's just slightly bigger. Yeah. So the question is, do you account for one edge or both edges? The answer is definitely both edges. So basically, what you're going to have, this calculation is on for the left edge of the output. So from the right edge, you have exactly the symmetry. So you will also get 3.7 for the right edge. Remember, the input is long, and then we're just talking about the calculation for each tile, right? So all the tiles in the middle will have 3.3, but then the very left edge tile and the very right edge tile will give you 3.7, right? Okay, very good. Now, things start to get a little bit dizzier, okay? So, this is one of the sort of the more, I would say, mathematical part or arithmetic part or algebraic part of the course. So in general, when we look at the internal tiles meaning the tiles other than the two edge tiles, the total number of global memory access, is replaced by the total number of global memory accesses. Is essentially tile width plus the mask width minus 1 n elements. And so essentially, you load tile width plus mask width minus 1 input elements, okay, into the shared memory. And then, if you look at the usage of the input elements into the shared memory, it's 1 plus 2, plus mask width minus 1. So these are the left edge, part of the input tile, and this is the middle part of the input tile, and this is the right part of the input tile, right? So this is just the symbolic form of a generalization of the small example. And then when we are faced with this kind of series, we resort to the mathematicians who have worked out the formula for the series, right? So this is one of the simple arithmetic series that we all learned. When you have 1 plus 2 plus 3 all the way to n is n times n plus 1 over 2. And this can be derived with a little bit of a triangle thing. Remember that the triangle thing that we all have used. And talking about life not being fair, right? We talk about life of these input elements that are not quite equal, and the input elements are used more or less. And the story is that Mr. Gauss, in the mathematics domain, apparently I'm the 13th generation student from Mr. Gauss. Okay, so if you look at the academic genealogy, you will see what the sort of you can just ask for someone, and then you can tell. It will say, okay, the genealogy goes all the way up to a particular person. So my line of lineage apparently goes back to Mr. Gauss. And so my advisor was, I think, is the 12th generation, and I'm the 13th. So, you know what, Mr. Gauss apparently derived this series when he was age of 6 going on to 7. We're not talking about 16, 17, okay? We're talking about 6 going up to 7. So life is truly not fair, okay? Let's just accept it, okay? On the other hand, the rest of us can still make contributions, okay? So, you know what, it doesn't matter, that we didn't derive a very important theorem at the age of 6. We all wish we did. But, by this time, you're capable of doing a lot more than Mr. Gauss when he was 6 or 7. Okay, so, take it and run with it. So, we take that series and say 1 plus 2 plus da-da-da all the way to mask width minus 1. So mask width minus 1 is the n now, right? And so, then so it's n times n, n times n minus n plus 1 divided by 2. N is mass width minus 1. N plus 1 is mass width. And then divide by 2. This gives you the first part. The second part is very, very easy. You just use the same thing. Mass width times the section, the length of the section, which is tile width minus mass width plus 1. And then the right-hand series exactly some symmetry of the left hand, so it's still also mask width minus 1 times mask width divided by 2. These two are the same, so you can get rid of the 2, you add them up, get rid of the 2, you get mask width minus 1 times mask width. And this side is still mask width times tile width minus mask width plus 1. And then you take out the mask width, okay? Your common factor of the mask width, you take it out, and you add up mask width minus 1 with tile width minus mask width plus 1. So these two items cancel each other out, so it becomes tile width. And this is exactly the same as the output view, but the output view is so much easier to derive because the output view says I have tile width number of output elements, and each one need to use a mask width number of inputs. I multiply the two, I get the total number of global accesses, right? So this is exactly what I'm trying to say. You can do it from either way, but pick the way that is easier for you, which for most of us, it's going to be the output view, okay? I went through all this trouble to derive it in the lecture simply because you're going to be seeing this kind of situation for many of your algorithmic derivations, in terms of algorithm complexity and so on. Oftentimes, for a given problem, you will have a simpler view, you'll have a more difficult view. And I learned this from Professor Karp, Dick Karp at Berkeley, and then he's one of the Turing Award winners. And when he was presenting the network flow algorithms, he showed us several times, how you can pick the right vantage point, viewpoint, and make sure that you have the right kind of invariance and so on, that you make things simple. Okay, so this is definitely one of those little examples. Okay, so if we look at use the beauty of this formula, because we're using tile width, mask width, and so on, then we can start to vary these numbers, right, and see some trends. Okay, so this is one of the trends that we can show. So for 1D, remember this is the formula, and the formula should be extremely easy to remember. The top is the total number of global memory accesses you need to make. So you have so many output elements, tile width output elements in each tile, and then each one will use mask width. So that's the top is easy to remember. The bottom is you need to load the input tile elements, and the number of input elements is tile width plus radius on each side. So that's mask minus 1, right? Okay, so that should be extremely easy to remember. You really shouldn't have to memorize it. You should be able to derive it now, just once you understand it. So let's plot out some numbers. So let's say if we take the output tile width and set it from 16 to 256. Small tile size all the way to big tile size. Okay? And what's the consequence of bigger tile size? You use up more and more shear memory, right? And then, so you can also have bigger and bigger mask width. So from 5 to 7 to 9. These are problem dependent, right? So your problem calls for a mask size of 5 or 7 or 9. So if we plot out these two dimensions and we, using this formula, we're going to get numbers. We're going to get some numbers. So for 16, if the mask width is 5, we'll get 4.0, and 32, 4.4, 64, 4.7, and 256, 4.9. Let's pause for a moment and think about the meaning of these numbers. What do you see? One of you may raise your hand and say 5. Yeah. Exactly. Whatever that mask width is. Absolutely right. This is exactly what engineers should do. Okay? So, does this surprise you? Shouldn't, right? Because every output element uses 5 input elements. So if we have infinite tile size, the effect of those elements on the edges should be very, very small. So all these output elements should be accessing their input from the input tile, and also each of them should have 5. Global memory access is replaced, right, by the shear memory contents. So that's why it's asymptotic, and you will never get to 5, but you get awfully close. Another observation: if we look at the mask width 9, things are slightly different. You start with 6, and then you go up to 7, 8, 8.5, and 8.7. Okay, so this tells you something. This tells you that when the mask width is bigger, you need to have bigger tile size in order to get close to your theoretical limit. Why is that? Because when you have bigger mask width, your halo elements become more important. You have more effects from your halo elements, right? You have more halo elements. And that means that you need to have a bigger tile to be able to offset the effect of those halo elements to get something close to 9. And so that's the insight here. For one dimension, the use of shear memory is actually no big deal. Okay, use of something like 256, and plus those elements on both sides. These are peanuts because we have 64K shear memory available in the streaming multiprocessors. So that's why it's a no-brainer that we're going to be using fairly big input tile sizes for 1D convolution. The flip side is that even though we get very, very large number of input elements into the output tile size and therefore input elements into shear memory, we're still going to be limited by the mask width. So no matter how big the tile size we use, if the mask size width is 5, you're not going to get more than 5 reduction. This is the reason why some people really don't like convolution. They're not like matrix multiplication, if you think about it. The matrix multiplication reuse goes up, goes up with the tile width. Remember that? 16 times reuse. 32 times reuse. It's a great scale. You just keep going up in terms of the reuse out of the shear memory. But for convolution, we're approaching the mask width. If the mask width given to you is 5, you're never going to go above 5. So that's why many of the convolution algorithms are bandwidth limited, simply because you cannot just use arbitrarily big tile size to increase your reuse beyond that point. It's set, the limit is set for you. Okay. Any questions? Okay. This is one of the most important things that you should get out of this class, if nothing else. Your data reuse for stencil type of computation is truly limited by the dimensions of your masks. Okay. Now, let's go into 2D. Okay. 2D is a little bit more pleasant And 2D is the reason why GPUs have been doing so well in machine learning and so on. And so this is exactly the fundamental reason. And so we're going to look at strategy 2. Strategy 1 and strategy 3 are similar. Okay, so strategy 2 is actually probably the most interesting analysis you can make out of this, most challenging analysis you can make out of the 3. So for strategy 2, remember we're going to be having enough threads to load all the input elements in one shot. Okay, every thread can just load one input element. Okay, and then when it comes to the calculation of the output elements, we're going to turn off some of the threads. Okay, and only use a subset of the threads to calculate the output elements. In the convolution, in the real convolution calculation. And then some of the elements, like this corner element, there's something quite dramatic, right? So we have 25. It's a 5 by 5 mask in this example, so we should be using 25 elements to calculate each output. But then, if you're at the corner, you only use 9 of them, okay? And instead of 25. So that ratio can be quite dramatic. That should tell you that some of these ratio and then this asymptotic curve will be more dramatic than the one dimension. Okay, so let's go through the calculation. So let's go to a small 8 by 8 output tile, 8 by 8 output tile, and 5 by 5 mask. Okay, this is a simple extension from 1D to 2D, right? We used to have 8 output tile and 5 input mask. Now we just raise it to 2 dimensions. So 8 by 8 output tile and 5 by 5 mask width. Okay, so very, very simple extension, generalization. So for the 8 by 8 output tile, we're going to have 12 by 12 input, 2 on every side, right? So for the mask. So we're going to have 12 by 12 input tiles. So these are 144 n elements that will be needed to load into the shear memory, okay, when we accommodate the input tiles. And the calculation of each p element needs to access 25, right? 25 input elements. It's a 5 by 5 mask. So the global memory accesses that we need to make in order to calculate the 8 by 8 or 64 output elements is 25 times 64, which is 1600. Okay, 1600 accesses. So now we're talking about real business. Okay, 1600 accesses. That's substantial. Okay, and then if we look at the reduction, we need to load 144 of these things into the shared memory in order to eliminate all the 1600 global memory accesses. So we pay 144 access, and then we are home free. We access all the, all these elements a total of 1600 times. So this reduction is much more attractive. 1600 divided by 144, now we have 11 times reduction. So this is much, much more substantial than the 1D case, okay? But for those of you who have been following, you will say, this is by no means the best outcome you can expect, right? Remember, the number of accesses, what's the number of reduction that you would expect if we have infinitely large input tile, output tiles? It will be 25, right? Because every element is going to use 25 input elements. So if we have every one of them into the input, into the tile, then the total reduction should be close to 25. Okay? It should be close to the total number of elements in your mask. Okay? So why not? We'll look at it very soon. So in general, we can also generalize the calculation. It's actually really, really simple generalization. So when we look at the input tiles now, the input tiles are tile width plus mask minus 1. So it's just wider in each direction. So it's tile width plus mask width minus 1 squared now, rather than just to the itself. Now just square it from input for 1D to 2D, right? This is just exactly the same expression squared. Okay, very simple generalization. And the calculation of each P element needs to access not just the mask width now, it's a mask width squared, because it's a 5 by 5 mask rather than 5 mask now. So you are replacing tile width square, this is the total number of output elements, times the mask width square, which is the total number of input elements every output element needs, right? And this gives you the total number of global memory accesses you hope to eliminate, to reduce by loading things into shared memory. And the number of elements you load into the shared memory is exactly the input tile size, right? So that's tile width plus mask width minus 1 squared. If you take the ratio of the two, you get the reduction. Okay, so this is the reduction formula. And if you look at it, compare that to the 1D case, it's exactly the 1D case squared, which makes perfect sense intuitively. Okay? So now, if we plot out these numbers, okay, we see that, so we're using this expression here, and then we say, okay, 8, 16, 32, 64, and then mask width 5 and 9. Remember, these things all need to be squared, right? So you plug that into these, this square formula and then plot the numbers. You see that for 5, you now see 11, 16, 19.7, and 22.1, right? So now you see that the input tile dimension need to go quite high for you to be anywhere close to the limit that you are expecting, which is what? 25, right? It should be approaching 25. But you say, why did I stop at 64? Don't underestimate the 64. The 64 is not exactly the number of elements you're going to place into the shared memory. It's what? 64 plus 4 squared, right? So it's going to be 68 squared. And that goes up very quickly, right? 68 squared is about 4,000 elements, 4K elements. 4K elements, 4 bytes each, give us what? 16K, which is already 1/4 of the shared memory you have. If you wish to have 4 thread blocks, if you really hope to have 4 thread blocks in a shared memory, this is already the limit of shared memory you can use. Does that make sense? So these numbers go up so quickly. That's why when you have these massively parallel processing processors, you're going to be playing with big numbers. And sometimes you'll be playing with squares of these modest numbers and then become very big numbers. Unfortunately, many of the science computing, engineering computing people are dealing with 3D, okay? So then you start to have these cubes, right? And these cubes go up so fast that your input tile dimensions are oftentimes limited to extremely small numbers. So if you go to Carl Schalten's group, when they build their molecular dynamics simulator with electrostatic maps and so on, you see that the number of input elements and output elements they can afford to have these tiles is extremely small, 4 by 4 by 4, okay? Up to maybe 6 by 6 by 6 or 8 by 8 by 8. These are the numbers that they play with in order to be able to use the GPUs for their computation because they are playing with 3D structures, okay? So again, if we use the mask width, bigger mask width, such as 9 here, then the ramping is even more obvious. You see that you start with 20, and then you have 36, you have 52, and you have 64. Where do you expect it to end? 81, right? But we'll probably never get close to 81 because it will be we'll be exceeding our shared memory way before that. Okay, so bigger mask width always gives you, bigger potential reuse, but it also gives you the kind of the, it also gives you a much, difficult time using sheer memory to get you that goal, right? You have a bigger potential payoff, but it makes it a lot difficult for you to get there, right? This is the irony of, these cloud algorithms. Does that make sense? Okay? So, this is one of those things I always tell people, when you listen to me, you will make sense, okay? You will walk out of this classroom saying that everything Professor Hu said makes sense, okay? Do a test. When you go home tonight, when you have dinner with your roommate, explain that to your roommate, okay? If you can explain to your roommate without any hiccup, then you're there. About half of you will have trouble, which is normal, okay? Don't feel bad. So go back, watch the video, do another practice, and then have another dinner with your roommate, explain it, okay? So until you can do it, because that's when you will really master it, okay? So trust me, if you have trouble with your explaining to your roommate, that's normal, okay? Go back and do it one more time. So you can also account for the ghost elements. Now the ghost elements can be on both sides. It could be on the vertical side, it could be on the horizontal side, and you can also have these corners, right, that will have different ratios. So it's a little bit more complicated than the calculation of the 1D, but it's a worthwhile exercise for you to to go through. It's not required, but it's something that I always encourage people to do. It's kind of one of those little entertainments that you can have over the weekend. It shouldn't take more than half an hour to get it, and but it'll be fun. Okay, you'll make your weekend much more pleasant. Any questions about convolution? I want to make sure that everyone is absolutely solid about convolution before we move forward, right? So, at this point, you should be able to write tile convolution algorithms, and you should be able to analyze exactly what kind of, memory access reduction you can get. And you're going to start with about 2 calculations per memory access for the convolution. Remember, the weights or the coefficients are actually coming from the constant cache. And then, with a 5x5 matrix and then with a reasonable shear memory for 2D, you can probably expect about 11 times of reduction. So you're going to be probably getting about 22 time calculations per memory access. And for both of these machines, it's still not going to be good enough, but it gets you about halfway into the peak. Okay, so these are the things that you can use to estimate how good, for example, the neural network implementations will be in terms of the number of the flop rate that you can achieve from each of these layers and so on. At this time, you are already getting into a skilled engineer. You will be able to have some very intuitive understanding of how fast the neural nets are going to run on these machines. Okay, you are at the point where you can start to think about these things in a rational way. So in the next 3 lectures, okay, we're going to be talking about neural networks, and so we're going to apply some of the things that you have already learned, and so that you will have a really good understanding of what a high-performance neural net implementation would look like. But before we do that, we're going to start by giving you a little bit of intuition about what you're going to get into in terms of machine learning in general, and then the deep learning neural net. What are the kind of important concepts that you need to keep in mind? This is not a machine learning class. Okay. I'm not telling you that once you finish this lecture series, you know enough about machine learning that you don't need to take a machine learning class. There are many more things that you really should learn about machine learning by taking a machine learning class. However, when you take those classes, they're not going to be teaching you the important computational techniques for implementing these kind of things. So this is what this course is about. Okay, and the lecture here is just to give you that bridge and that foundation so that you can learn about it even without taking a machine learning class yet. But it doesn't mean that you know so much that you don't need to take a machine learning class anymore. So this lecture is contributed by Carl Pearson last semester. And Carl is my PhD student. And he is one of the Mavis the faculty fellows. And he's one of the students that we're cultivating to be a professor soon. And so as part of his fellowship program, he developed a series of lectures for 408 with me. And then I want to make sure that I recognize his contributions. And so we're going to start with some of the basic concepts that that lead to the computation that you'll be doing. So for those of you who have already taken the machine learning classes, the machine learning class, machine learning can be taught in different perspectives. And so from our perspective, it's an important way of building applications whose logic is not fully understood. Okay, so we don't know exactly how to do certain things, and in order for us to be able to write a piece of algorithm code to do a particular task, we need to know exactly how to do it, and then we break it down into steps for the computer to do it. So this is a typical way of designing algorithm code in our computing systems. But there are many things that we don't know about exactly how to do it. And we have something called heuristics, and in some cases we have some kind of rules, but these things are not in general agreed upon. So there's not a well understood way of doing these tasks. So we resort to something that humans do, learn by examples. Okay? Whenever we don't know exactly how to do certain things as humans, we oftentimes tell people, you learn from examples. So that's why when people, oftentimes you will hear comments like, I cannot tell you what X is, but you will know when you see one. Okay, some of you know exactly what I'm talking about, right? Go on the internet, you will know what that X usually is in the, in the public, in this kind of, the popular press. So here is also this. We give you a whole bunch of examples, and we label them. Okay, we label them and say, whenever you see something like this, it is this. Whenever you see something like this, it's that. So if we teach you enough examples, at least you will be able to, to make that judgment correctly once in a while. So this is not exactly the most efficient way. And for example, think about this. If you teach addition by example, you say, okay, here are the examples. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. And then 2 plus 1 is 2. 2 plus 2 is 3. 2 plus 2 is 4. And you can just keep doing this, right? And conceptually, you can actually teach enough examples for most of the practical cases, if you think about it, right? You can probably teach enough examples for people to be able to do addition in most of the daily routines. But as soon as the numbers get big, right, you start to get into dicey areas. And there are also some, some, I would say, danger in this kind of case. For example, you may be able to teach division by example, okay? So if I teach division by example, let's say if I take 16 divided by 64, what's the number that you think it is? It should be a quarter, right? And, but if the student try to generalize that and say, okay, whenever I have two numbers, one on top, one on the bottom, 1, 6, 6, 4. Whenever they have two identical numbers, I can just eliminate them. So 1, 6 becomes 1. 6, 4 becomes 4. Right? Oh my God. That generalization is very dangerous, isn't it? Right? So be careful with these things. This is the fundamental danger of machine learning. when we try to use these data and generate rules, if we don't have sufficient number of data, we can overtrain. Okay, that's called overtraining. Okay, we start to to generalize some of these rules that really shouldn't be there because we don't have these counterexamples for some of the rules that we attempt to generate. Okay, so we use label data, the data that come with input values and their desired output values. And then we capture each label data item by adjusting the program logic. So we have something in the back and say, keep observing these input and output pairs, and we keep adjusting the logic until we reach the point where you give us some kind of input, the logic will give you some kind of output. Hopefully not just by eliminating the 6 from the expression. Okay? So that's the fundamental concept of machine learning is just learn by example. And what I told you about is called supervised learning. And then there are also unsupervised learning that could be a little bit better, but then you need to go into the the machine learning classes to learn the sort of to learn. This is now to not machine learning learn for you to learn some of the intricacies of supervised versus unsupervised learning and so on. Okay. That's not my job in this class, okay? So let's, kind of look at the machine learning, from the high level, what are the kind of, tasks or what kind of things that we want the computer to be able to learn to do, the logic need to be, be able to do based on the data. So the first kind of, tasks is classification, okay? This is probably the most common commonly mentioned functionality of machine learning algorithms. So which of the K categories an input belongs to? You give me an input, and then I tell you which category it is. For self-driving cars, whenever you see something, you say, okay, is this a pedestrian? Is this another car? Is it, an animal? Is it, something else? It could be a little bit of speed bump, right? You either stop the car or you kind of go slowly over that bump. And is that a bump or is that a person lying on the floor? Okay, now that classification is important in some cases, right? So you want to be able to classify things properly in order to make that decision, right? So that's classification. There's dire consequences when you do these kind of classification. Regression. Essentially, you predict a number of value, the value given some input. Whenever someone gives you an input, you say, okay, what is your prediction of, what's going to happen? So this is based on a experience. So you say, okay, given today's temperature or the past few days of temperature, can you predict tomorrow's temperature, right? So this is purely based on pattern. And we all know that, the modern weather forecast does not do that alone, okay? The modern forecast actually use physics simulation and CFD and multiphysics and so on to predict how fast the weather systems move, okay? And then how they form and so on. And, not just from the numbers that you get from each day to predict the next one. But if you don't have that, option to go into the detailed physics, this is the best you can have. Then you can gather the data, hopefully from the past 50 years. And then you may have the sequences that are based, that correspond to different weather systems and so on. Hopefully those patterns will reflect in some degree, to some degree, okay, that you can get from the weather simulation. Because empirically, you may be observing these sequences with different weather systems and so on. You have enough that experience, you might be able to predict with some accuracy. Does that make sense? Okay, so that's regression. Transcription. You want to be able to take unstructured data into texture form. For example, you may have a handwriting, and you may have a, let's say, scanned document, and then you want to be able to generate the text form of that scanned document. So optical character recognition, and this is, you can give it a huge number of these, scanned characters, and then what the text ASCII code that you're supposed to generate, and hopefully you have enough of that to be able to, to generate the text document that you can get, so that's the optical character recognition. Translation. You want to be able to convert a sequence of symbols in one language to a sequence of symbols in another language. Google Translate, right? So that's one way. And then you can have structured output. Essentially, you want to be able to convert from input to a vector with important relationships between the elements. This is actually the most valuable part of machine learning. In reality, this is actually what most of the CEOs want from machine learning. Basically, you have unstructured data, meaning that you collected all kinds of things about your customers and so on, but these things are not in the form of a database with well-defined columns and well-defined attributes. So you want to be able to learn from the input data that you could collect, the sales, the purchase, the history and so on, into some kind of numbers that you can use for your business. For example, for January, how many items I should have for my inventory, right? And so these are the structured output that you want to be able to get out of your unstructured sensing and history data. Natural language sentences into a tree of grammatic structure. So when I tell you all these words in a sentence, can you classify these words into subjects and objects and verbs and so on, that I can begin to really understand what the person is trying to say, rather than just a collection of words, right? And others, anomaly detection, synthesis, the sampling, imputation, denoising, density estimation. These are usually combinations of the previous tasks. Okay. Now, so why machine learning is so hot today? Machine learning has been around for a long, long time. Okay. Ever since I was in grad school, you don't want to know when. Okay. So you were not even born, most of you. So when I was in grad school, machine learning was hot for a while, and then they cooled down. Okay. And neural net was really hot when I was in grad school for a while, and then it went down. Okay. The reason why these things were not really used in big time is because the computing hardware back then was not able to economically process a very large amount of labeled data to give you the ability to do these tasks in a reliable way. Just like the addition, you need to have enough of those examples. If you don't know the true rule of addition, you need to have enough of those examples to be able to handle the daily addition needs. Okay, so when we had the GPU computing hardware and the programming interfaces such as CUDA, that enabled the processing of very large amount of data. Okay, and that is actually enabled very fast research cycle for deep neural net training, and that happened in 2012. Okay, that was the time when machine learning and neural net started to really take off in the industry, if you look into history. And that was 4 years after the first introduction of CUDA GPUs. Okay. And the computer vision, speech recognition, document translation, self-driving cars, data science, all these things were research areas where people spent years and years trying to come up with algorithms, trying to come up with the heuristics and so on, but not very successful. However, with a huge amount of training data, now you can learn these heuristics and algorithms using the machine, rather than poor grad students sitting in front of the desk and trying to do each heuristic. And that was the fundamental change that happened. The machine now does the hard work to create the logic that you want. So most involved logic that were previously not effectively constructed with imperative programming, algorithm design, heuristic design. So using big label data to train and specialized deep neural net-based classifiers to deriving a large quantity of quality label is actually a challenge today. So if you look at the industry deployment of deep learning, whenever there's a cheap way to produce very high quality, label data, such as ImageNet, okay, then you have very, very effective, deep neural net based, image recognition modules. But if you have something that requires very high cost, for example, if you want to train a medical imaging, let's say a cancer detection, neural net, the people who make that kind of label data are not paid by 30 cents an hour, okay? Those are the people who are paid much higher than me, okay? So generating a very large amount of data for that kind of application is economically much, much more difficult than, the kind of the ordinary object detection. So we're going to, to go into this in more detail next time. So basically, we're going to start with classification, and then we're going to go into some of the formulation. But before, next time when we pick up, I'm going to go back to binary logic in the most simpler form, and then correlate that to the abstraction here, and go into the computation. Okay, so see you on Thursday. Oh, by the way, I'm going to stay in town on Thursday for this Thursday. So I will be giving lecture here, but we'll be experimenting with a way for the Chicago students to ask some questions. We're going to try to work out a mechanism so that, so Thursday I'm still going to be lecturing from here. Okay.